Welcome to a hangout from the SETI Institute, where we try and learn more about the existence and the potential for life beyond Earth. I'm Seth Shostak. Today we're talking about new results from the Kepler project. There have been new planets announced, including some that look like they might be hospitable to life. Now, joining me today for this hangout are three SETI Institute scientists all connected with the Kepler project. And to my left, we have Joe Twicken, Joe, and we have Doug Caldwell and Jeff Coughlin. And these guys are going to fill you in on the latest and the greatest about this very exciting discovery. So let's get right into it, guys. Kepler, without doubt, the greatest exoplanet finder of all time. What's the tally on candidates so far?
So we're up to 4,969 candidates, just shy of 5,000.
And how many have been recently added?
We just added over 500 additional candidates.
Okay, but is that because there have been new observations, or are you analyzing more data that already existed? I mean, 500 is a lot. That's more than 10% of the total.
Yeah, it's a good number. And so it actually turns out we only have one extra month of observations to look at with this latest catalog. And that's the last month of observations that Kepler took. And so we're basically finding new planets now, not due to getting more observations, but due to being able to dig into the data better. So we're able to pull out those planets.
Okay, now I'm asking all of you, how many of these are confirmed planets? Because they're called candidates, and just as in politics, just because you're a candidate doesn't mean you actually get to sit behind the desk.
One of these is confirmed. That would be Kepler 452b.
And how do you confirm that? I mean, normally, doesn't that require somebody else to go to another telescope?
It does. There are several ways to actually confirm. The gold standard is to go out and measure the mass with another method, and then you know the size and the mass of this thing, and you can say for sure it's a planet. For a lot of these Kepler candidates, they're really just too small that they're beyond our ability now to measure their mass. So what we can do is take additional observations of their star, better understand the properties of the star and the planet, and then try and say, how likely is it the signal we're seeing is a planet versus some other possible false positive that's spoofing us?
And you have no doubt about 452b?
We're confident at the above 99% level that it's a planet signature that's causing the signal we're seeing with Kepler.
Why don't we get into some of the properties of 452b? How far away is it? That sort of thing. How big is it?
1.6 Earth radii. I think it's 1,400 light years.
Yep.
1,400 light years away.
1,400 light years away, okay. And each light year, about 6 trillion miles. So you can multiply those numbers together in your head. I'm sure they've done that already. All right, this is a long way away. We're not going to go visit this place. Can we even see this planet with any telescope we have or will have in the next 5 years?
Not right now. It's the host star is so faint, it's so far away from Earth that we can't directly image it right now. Maybe missions tens of years from now, but even then, this one is quite far away. We may not get a lot of follow-up data on it.
But Joe has just said it's 1.6 times the diameter of Earth. It would take you, 35 hours to fly around it in a commercial jet, right? How do we know that number if we can't see it?
Well, we make these measurements by observing the transits of these planets around their host stars. And so we're able to very accurately determine the size of the planet relative to the size of the star.
Okay.
And we determine the size of the star by doing follow-up measurements of the star, and we do modeling to determine its properties based on the temperatures and the surface gravities that we can measure.
You say 1.6 times the diameter of our own planet. What's the uncertainty in that? It's what, 10%, 20%, 50%, 100%?
I think it's of order about 10%, and it really depends on the uncertainty with how well we can measure the star's properties.
Okay. A new catalog has come out.
That's right.
Jeff, new Kepler catalog. It's not the first of the Kepler catalogs.
Nope. In fact, it's the 7th of them.
Oh, okay. Why should I buy this catalog? Maybe I have the first 6.
Right?
What are you promising me in this new catalog, and who would buy it anyway?
That's right. So one of the great things about this new catalog is it's the first one to be based on the entire Kepler mission data set on the original field. And we've really improved our analyses. One thing we've done is we're now moved to a fully automated method. And so we've been able to assess every transit-like signal in the data. And that includes stuff that we found early on in the mission with only a few months of data. Now we have 4 years to look at it. So this catalog is now the newest, most reliable, best catalog we have out there.
Okay, and how do you get this catalog? I mean, can you order it on Amazon?
You can. Well, you can send me a check or money order. Yeah. No, all the data is publicly available. So if you go to the NASA Exoplanet archive, you can actually look up all these planet candidates that we have.
And okay, and so this catalog has more than 4,000 candidates in it. It
That's
has
right.
the parameters insofar as you know them.
Mm-hmm.
And who's going to look at this catalog? Is it just going to be other astronomers?
No, anybody can look at it. The public's interested, and if they want to take a look, but The main use will be astronomers doing hard statistics, trying to find out how many planets are out there in the galaxy, especially those like Earth.
Okay, so in the early days of exoplanets, back in the 1990s, they find an exoplanet. The first one was found in 1995, and it was kind of like Jupiter size. It was a big thing.
Mhm.
And for a long time, the planets that were found around other stars were what were called hot Jupiters. That sounds like something you get out of a gumball machine or something. But hot Jupiters turned out to be big planets very close to their host stars. You've got a catalog with thousands of planets in it. Are they mostly hot Jupiters?
No, I'll keep going here, but turns out that hot Jupiters are actually kind of rare. They were the first ones we saw when we started looking for planets 20 years ago, but that's only because they're giant. They make a whopping signal that's really easy to see. It turns out that the most common types of planets out there are small little rocky planets just like Earth.
All right, so small rocky planets. What about planets like this one? This is not quite the size of the Earth. It's between 1 and 2 times the size of the Earth. There are a lot of those, or am I wrong?
There are a lot of those, and they're also very common, and they were somewhat of a surprise based on what we knew about our solar system, where we don't have anything like that. And so we're struggling to try and understand what the conditions on these planets might be. And there's a handful of these that have been discovered where we were actually able to measure the mass and the radius. And from those measurements, we can get the average density of the planet and start to try and understand what's it made of. Is it mostly rock? Is it iron? Is it mostly hydrogen and helium? And so it's using these models of planet composition that allows us to say that Kepler 452b has a better than even chance of being rocky. We don't know for sure. It could be much more gaseous, more like Neptune, or have a lot of hydrogen and helium. But it also could be rocky, and the models indicate that it's got a slightly better than even chance of being rocky.
Okay, but to be clear about this, we don't have what are called radial velocity measurements of this particular planet. So we don't have a direct measurement of the mass.
That's right, we do not.
Okay. All right. Okay.
The radial velocity signature of this one would be very small. I think it's something like 45 centimeters per second. So the star is moving only a very little bit because of this planet.
I think ants move faster than that. Yeah. Okay. So that's very good. Now, but this class of planets that you described that are between 1 and 2 times the diameter, if you will, of the Earth,
Mm-hmm.
some people call these super Earths. Sounds like a Marvel Comics superhero or something. Super Earths. I think you guys don't like that term.
I mean, that term implies a lot. The people read a lot into that term, and other people call them mini Neptunes, and they're sort of the super Earth mini Neptune camps that are fighting it out to what best describes these planets. And I think the most we can say is that there's a continuum of planets between things that are rocky like the Earth with a solid surface and things that are more like Neptune that have a lot of gas and volatiles. And this falls somewhere in that continuum.
What could a super Earth be like? I mean, could it really be a gas ball, or is it much more likely to be something, made out of metals and dirt and the kind of stuff that our planet's made out of? I mean, is it really a cousin of Earth, or is it something that if it walked in the door, you wouldn't ask it to stay for dinner? I mean, it's not a cousin at all.
I think at the smaller end of that range in between Earth and Neptune, they probably are a lot like the Earth. You can add more rock and material to the Earth, and it'll just get bigger and look like the Earth. And it's only when you start to get a lot more massive that the planet's able to hold on to a lot of the gas that's around when the planets are forming, and you end up with something looking more like Neptune. And the size of this planet at 1.6 is kind of right around the transition between where models say you're going to end up more like Neptune or more like the Earth.
Okay, so there is still some chance that it's a kind of a gas ball.
Yes.
Yeah, but that it might float in water the way Saturn does, right?
We don't know the mass, so we don't know the density.
Okay. What about the possibility that it's a water world? Sounds like a bad movie, but water world, they just got oceans everywhere. There's no land anywhere. Is that possible?
Sure, it's very possible. Yeah, it's interesting. If all you have to do is raise the water level on Earth, a couple thousand feet, and we would be a water world. It's kind of amazing that we actually have a planet that's a nice mix of rock and water.
Yeah, so it's possible. And I'm sure that many people are going to be asking themselves, if not you, because they're far away, but, well, how are we going to know? How do we know whether this planet, okay, it's a candidate for being inhabited, but we don't even know if it has oceans or an atmosphere. So how are we ever going to know that? Are we ever going to know that?
For this particular planet, we'll probably never know that. But one of the follow-up missions to Kepler is TESS, which will be surveying all the brightest stars in the sky, which are presumably the closest to us. And the idea is to identify 50 small planets, obtain their masses, and these would be the prime candidates for follow-up to actually measure the composition of their atmospheres with the James Webb Space Telescope, which
Well,
is supposed to launch in, I think, 2018.
Yeah.
Okay, well, following up on that, Joe, you know, surely the significance of this planet is to show that these kinds of planets exist, right? But does it also give you a better handle on what fraction of the stars out there in the night sky have a world kind of like this one?
That's exactly the purpose of Kepler, was to determine what fraction of stars in the night sky have a whole range of different planets, in particular habitable planets, but not necessarily only habitable planets.
So what's the answer?
Oh, so we're working on that.
Yeah, so right now, I mean, we have, there are some studies out there that are trying to tackle this question. And the ranges really right now seem to be 15 to 25% of stars have a planet of a similar size and similar distance, you know, to be in the habitable zone like Earth. But a lot of those studies are based on stars that are a lot smaller than our sun, so-called M dwarfs. And so what's interesting with this new catalog, and especially with Kepler 452b, what we're finding is that that number doesn't just apply to the M dwarfs, it does seem to apply to the G dwarf stars like our sun.
Okay, but that number for the M dwarfs, if I recall correctly, a preliminary analysis suggested somewhere between 15 and 55% of all M dwarfs would have something in the habitable zone, right?
Right.
And you're saying for sun-like stars might be the same?
Yeah, that's what we're starting to see indications of. You know, the catalog's just come out, so people need to do the hard work to really nail down the number, but initial indications seem that that's about right.
Okay, but that's astounding. I mean, because if you'd ask anybody, including, you know, astronomers, never a good idea, but if you'd done that, you know, 20 years ago and said, well, what fraction of stars you think have a planet that's sort of like the Earth, they might have said, well, we don't know, but maybe 1 in a million, 1 in 1,000. It sounds like it's more than like 1 in 2 or 1 in 5 or something like that.
Yeah, that's really amazing thing. That's exactly right. We really know it's not 1 in a million or 1 in 1,000. It's 1 in 10 or greater.
You guys aren't smiling. Why aren't you smiling?
It's great. I mean, I think that, you know, we love finding these interesting planets and talking about them, but the real legacy of Kepler in the years to come is going to be that number. What fraction of what kinds of planets are out there? And that's the real important discoveries that Kepler's making.
A year ago, there was a lot of media play for another Kepler discovery, planet Kepler 186f.
Yes.
And that was even closer in size to Earth than Kepler 452b, right? Has the new discovery kind of displaced that one as being at the front of the class in terms of being closest to our own world?
Well, again, the unique thing about this one is compared to the Kepler 186f is that 186f was around a really small M dwarf star. And there's nothing wrong with that. I mean, I got nothing against M dwarfs, right? But we orbit a G dwarf star, and the one place we know that has life is right here on Earth. So if we're looking for other worlds out there that might also have life, you know, makes sense to search around G dwarf stars. And so that's the big point of Kepler 452b. It's the first one around a G dwarf.
Okay, but you're prejudiced toward G dwarf stars, right? I mean, everybody likes the sun.
isn't? Yeah.
Well,
It is the primary goal of the Kepler mission to identify habitable planets orbiting sun-like stars.
yeah, okay, that was the brief given to this mission, right?
That's right.
You know, when it was conceived more than a decade ago now, right? Okay, but that was an era in which we figured that M dwarfs, you know, the little runty guys, the runts of the cosmos, you know, they wouldn't be great for life because you'd have to be in a planet that was too close, and there were a lot of problems with that. But I mean, if you were writing the brief for Kepler today, would you limit it to G-type stars, Joe?
No pressure.
I would.
Yeah.
No. I would.
You would. Why?
Why wouldn't I? No. Well, Jeff already said that, you know, we know that we're here and we orbit a sun-like star, and it's definitely possible for life to evolve under these conditions. And M dwarfs, maybe not.
Well, I'm going to push this just one more notch, because 3/4 of all stars are M dwarfs, right? It's like critters. There are a lot more of the small guys than there are the big guys. I mean, you worry about the big guys, but there are a lot more small guys. So if an M dwarf has the same probability within a factor of 2 of having a habitable world, shouldn't we be spending a lot more time looking at M dwarf, you know, exoplanets, and forget these G-type guys?
Well, it's a good idea. I don't think you want to forget the G-type stars, but looking at M dwarf stars is a good idea. In fact, K2, so the Kepler mission that's been repurposed to look at different fields aside from the original one, a large fraction of the targets are M dwarf stars, because if you look at an M dwarf star, you can have a planet that's much bigger relative to the star. It's a big whopping signal. They're easy to detect, and they're easy to follow up if they're close. So yeah, you know, we are looking. We're certainly not ignoring them.
Yeah, and if they're, you know, 3/4 of all stars are M dwarfs and only 10% of all stars are G-type stars, right?
That's
Then
right.
the M dwarfs, you know, the nearest 1,000 M dwarfs are a factor 2 closer than the nearest 1,000 G stars. So it sounds like something to look at. But you guys don't discriminate. I mean,
No, part of the problem is M dwarfs tend to be very faint. So Kepler, which was staring at one field of view, didn't have all that many that were bright enough to detect. With K2, we're able to look around the sky and pick out more of these M dwarfs. And the test mission, which is slated to launch the Transiting Exoplanet Survey Satellite, is going to do an all-sky survey, and it'll be able to cover all the nearest stars, most of which are going to be M dwarfs. So it really will have more focus on these smaller stars.
Okay, and I'm sorry.
Oh, for K2, we're looking at any particular part of the sky in 80-day campaigns. And if you want to find habitable planets in 80-day campaigns, then your only chance is to find them on M dwarfs.
That's a great point.
Because you need, we require 3 transits in order to define a transiting planet signature. And you won't get 3 transits in 80 days on anything but an M dwarf.
Yeah, well, that brings up a point we didn't cover, and that is the orbital period of 452b. I believe it's rather close to 1 Earth year,
385 days.
385 days. So I'd be younger if I.
That's right.
Oh, okay.
Slightly.
But you'd weigh more, Seth.
Well, that's hard to imagine, actually. But okay, that's great. Okay, all right. You know, I have to ask this. Kepler has stopped doing its original type of survey, but we lost that last servo mode or whatever, the reaction wheel there. So it's not doing that. It's moved on to tests, as Joe has just described. Is it fair to say that the enormous harvest of exoplanets we've seen in the past couple of years, thousands of them, is that harvest done? Can we all go home and watch TV now?
Yep, we're gone now. No, really, the answer is no, not by a long shot. You know, we just got this data set, and part of the problem is that when you get data like this, that's brand new, that's cutting edge, and it's pushing the limits, you really need to spend some time studying it. So we've learned a lot over the past several years about the data and how to really tease out these planets. So it's just now we're starting to develop the techniques to get to them. So a year from now, we're going to release another catalog, an 8th catalog, and we really expect that one to contain even more planets, especially those interesting small ones in the habitable zone.
How are these catalogs doing? Have they reached the New York Times bestseller list?
Yeah.
I hope they have. Okay, so there's more to come.
There's more to come.
There's more to come.
One more to come. There'll be one more catalog.
One more catalog.
next year.
Yeah,
We're running the pipeline one more time right now. And it's more sensitive to small, cool planets than ever before.
And aside from tests, what are the follow-up plans? What's going to do this again?
Well, let's see. There's the test mission, and then there's in terms of surveys, there's also a lot of great ground-based surveys out there that are looking for planets. You're going to have the Large Synoptic Survey Telescope come online. We'll survey the whole night sky, basically every night, and so we'll expect to find, I think, some more planets in that data. But for the sensitivity that Kepler has to Earth-sized planets transiting their stars, I don't think there's really anything on the drawing board right now to replicate it.
I mean, the European Plato mission might get close depending on how they operate, but that's you know, sort of 10 years off. I think NASA's long-term goal or you know, medium-term goal is we built and launched Kepler to determine, are these planets out there? And we don't know the exact number, but we have a really good idea that yes, they are out there. The next step is, let's find some of these planets that we can actually go and directly measure their atmospheres if they have them. And that's TESS to find them, and then JWST to measure them. And then beyond that, there are additional large telescopes that that are on the drawing boards to do the next step, take a detailed spectrum of some planet atmospheres, try and look for biosignatures or other signs that there might be that they might be inhabited, not just habitable.
You know, you wouldn't.
Yeah, so what you're saying, Doug, is we're moving from the era of reconnaissance to examination in some sense.
Yeah, I think we are.
And that's where we ought to go. You think the data are in hand now to answer the big questions: what fraction of stars of this, that, and the other type have this, that, and the other kind of planet?
I mean, certainly there are holes to be filled in, but yeah, we have a preliminary answer now that we didn't have 10 years ago, and that's very interesting.
All right. Well, then my final question to you guys is this. This is pretty exciting, but then again, a year ago we could have had this hangout, and it would have been pretty exciting.
Oh,
Kepler
sure. 186F,
right? We would have been talking about that. Are you anticipating in the next year that we'll have another hangout that'll be even more exciting than this one?
Do we have to wait a year?
Yeah, I know, a whole year. No, I really do anticipate it. Some of the new candidates we found are possibly maybe even smaller than Kepler 452. You need to do the hard follow-up analysis to really confirm it. But yeah, I think we're going to keep finding new planets, and over the several years, we'll keep finding better and better stuff out there.
Terrific. Okay, Jeff Coughlin, Doug Caldwell, Joe Twicken, thank you guys for being with us. thanks to all of you for joining us as well. Oh, wait, don't go away. Sorry, there's feedback. Okay, several of you have sent in questions. If I can read Lee's handwriting here. How long is it going to take before we can measure the atmospheric compositions? We sort of touched on that, but
yeah, I think for these particular planets, it's a long way off. But the hope is that with this test mission and then James Webb coming up, we will be able to do it for nearby planets that are like these, and that's going to be test launches in 2017, James Webb in 2018. So look for results, in 2020 or something. 5 years.
5 years. You're an optimistic guy.
Yeah.
Okay. Another watcher, listener, what are they on a hangout? Hanger on? Right. It's been mentioned the planet it more than likely does not have life. Why? Who said that? Did anybody say that?
We didn't say
After
that.
We didn't say that. Okay.
We don't
but
know for sure.
We don't know for sure.
Yeah. But the further addendum to this question is, well, why don't we search for life with our radio telescopes? And I can tell you, yes, strictly only here, we've only heard it here, that the Allen Telescope Array has already started looking at Kepler 452b, and we've examined it, over 2 billion channels of the radio dial, approximately between 1 and 7 gigahertz, if that means something to you. So 2 billion channels, and so far the 452 BENs, if they are there, have remained coy. So once again, gentlemen, thank you very much. Thank you for watching.